Hello, my fellow Almontians, and welcome back to another broadcast from the bunker. It's a beautiful day outside. I hope you guys are absorbing some sunshine. All right, let's jump into it. We're going to a new topic today, right? The long-awaited topic of plate tectonics. We're going to talk about the layers of the earth beneath our feet, right? How Mother Nature manipulates things and causes earthquakes, tsunamis, volcanoes, all sorts of exciting stuff. All right, so that's the next topic we're going into. Let's hit the do now questions, 25 to 27, and I'll meet you back here in a bit. Okay. Number 25, which statement best explains the apparent daily motion? Underline that word daily. If you're talking daily changes, that's got to be rotation. Stars around Polaris. So why do these stars go around Polaris? It's got to have to do with the Earth's rotation. And there it is, choice C. All right, number 26. Any brave volunteers on 26? No volunteers? All right. The moon has more surface craters than the Earth does because the moon has blank. How come Earth doesn't have as many craters? Well, there's a couple reasons here, but we'll address this one first. A big reason a lot of the meteors don't hit the Earth is because they burn up in the Earth's atmosphere, right? And, of course, the moon has no significant atmosphere, so as the meteors come into the moon, they just hit the surface. They don't burn up. Also, remember, about 70% of the Earth is covered by water, so had a meteor hit, 70% of it would be covered, of course, by water. So, yes, the moon is often referred to as the Earth's attic. If you get a big meteor shower, which this week there will be some meteor showers, oftentimes the moon will get hit as well, and even though you can't find them on Earth, you can certainly have a record of them on the moon. That's why they call the moon the Earth's attic. All right, so no significant atmosphere. And 27, let's see here. Which statement about the period of revolution of the planet is correct? Looks like you're comparing here, so we got to do process of elimination. Planet X has a longer period of revolution than Y. Well, where's X? It's closer to the sun, so it would have a shorter period of revolution. That's out. Z has a longer period than X. Z is way further out, so yes, it would have a longer period than X. That looks like it's correct. They will not be equal, so C is out. So far, we're still B. And Y has a longer period of revolution than Z? No, Y is closer to the star, so it will go around faster and have a shorter period of revolution. So we got to go with choice B. All right. Any further questions on those? Remember, type them into the comment section or shoot me a question on Remind. Let's jump back to the lesson here. Okay. So we're talking about layers of the Earth, what's beneath our feet. Now remember, we can only dig so far, right? The deeper you go, it gets just too hot, too much pressure. We can't physically get all the way down there. So it's called inferred properties, big word right there, inferred properties of Earth's interior, because we base it off of mostly seismic data. And we'll talk about seismic waves, P and S waves, a little later on. But we infer what's beneath our feet based upon how seismic waves behave. And this lesson presents, the accepted ideas of what is beneath our feet. I want to start out with a really great song here. Here we go. Oh yeah. Below the surface, throw your hands up and let's discuss the inner core, outer core, mantle and crust. Throw your hands up for the layers
surface. Throw your hands up and let's discuss the inner core, outer core, mantle, and crust. Yeah. The layer we'll discuss first is the central inner core in the center of the earth. A solid ball buried below the dirt.
We believe it's primarily metallic iron.
You can never take a trip to the inner core, right? The heat will burn you up 9,000 Fahrenheit, 4,000 miles below the Earth's crust. One down, three go, y'all. 1,800 miles from the tip top. The outer core is hard at work and it don't stop. It's busy spinning around the inner core. This steady movement causes Earth's magnetism. Ranging from 4 to 9,000 degrees, it contributes 1/5 of the heat flowing to you and me. It's liquid metal, the violently flow. So let it settle when you're ready, let me know. Just hands up for the layers of the earth. All up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle, and crust. Throw your hands up for the layers of the earth. All up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle, and crust. The middle layer is the largest of the class, about half of our planet's mass. The mantle is composed of very hot dense rocks that move and flow, always on the go. They never lie, never stop, and responsible for tectonic shifts.
Please believe.
Earth's plates are adrift. It's pretty thick, y'all, and the heat is awesome. 1,600 at the top, 1,000 at the bottom. The continental crust surface is where we breathe. A lot of rock up to 25 miles deep. The oceanic crust is just next door. It's 3 to 5 miles thick below the ocean floor.
Earth's surface.
70% H2O.
Where you get all that water?
Salty sea flows, fresh water in the glaciers, ice caps, and snow. Throw your hands up for the layers of the earth. Roll up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle, and crust. Throw your hands up for the layers of the earth. Roll up for what's below the surface. Throw your hands up and let's discuss the inner core, outer core, mantle, and crust.
Good stuff, folks. Good stuff. If you need to hit pause and rewind that a couple times because you enjoyed that so much, I understand. Here we go. How do we differentiate between the inner layers of the Earth? Well, this is a classic reference table diagram. And, you know, we'll zoom in on this, of course. But every time you hit a black line, that's a boundary, another layer of the Earth you're crossing into. And when you do, you're going to have different pressures, different temperatures, different densities, different compositions. It truly is a pretty wild place down there, folks. So we think. All right, so let's do it. Little color to the chart. It is on page 10, I believe, in your tables. Well, let me click on refresh my subtitles here. See if they'll start working. Testing, testing. There they go. All right. So here we go. First, we're going to zoom at the upper part here. Please make sure you're following along on your reference tables, because I'm going to point out different things. Okay? First off, the place that we walk and talk, with a mask nowadays, we call it the lithosphere, the upper portion. And that's us right there, the lithosphere. And the lithosphere includes the land you walk on, but also the land that the ocean water sits on, right? That's all the outer crust. The water just kind of sits on top. They call that the lithosphere. It is the thinnest layer of them all, as you can see, even though we certainly can't dig or even drill through it. Just can't happen. We melt the bit as you try to get deeper. All right, below that is your asthenosphere. They call it a plastic mantle. It kind of behaves like Jell-O. It's not really a liquid, not really a solid, but it does seem to have convection going on because it's much, much hotter below it. Keep going down, you go through the mantle, and all of a sudden you get to the next boundary, the mantle outer core boundary. The deeper we go, the hotter and denser it's getting. Keep going. You're at your inner core boundary, and finally, of course, the center of the Earth, it's about 6,400 kilometers down. And you've heard the expression, you know, if you keep digging, you'll dig to China. Well, obviously, physically we can't do that, but theoretically, if you did go through the Earth, you would come out the other side, and of course, whatever country is there, you would kind of pop out of the ground. So yeah, that's a little cross-section of the Earth there. This funny word up here, moho, is an abbreviation. The scientist's name was Mohorovicic. That was his last name. And he came up with the idea that the thickness of the crust is inconsistent, right? It's called the Mohorovicic discontinuity. Say that fast a couple times. But anyways, the idea that the continental crust is thicker than the oceanic crust. So let's double back. The continental crust is made out of the igneous rock granite, right? Granite is a felsic, lower density igneous rock, whereas the oceanic crust is made out of basalt, right? And basalt was the darker, denser, mafic rock, and it also happens to be thinner. All right, so that's what it's talking about, the moho there, the differences in thickness between the continental and the oceanic crust. Talk about depth. On the bottom, or the x-axis, you're going from 0, which is 0 deep, right? 0 kilometers deep, that's where we are. And you dig until you get to about 6,400 kilometers down. That's the center of the Earth right there. Notice what happens to temperature as you dig deeper into the Earth. It's off the charts, folks. If you remember lava, right? That cherry liquid that melts every material we know of on Earth. Lava's about 2,000 degrees. Well, if you went deeper into the Earth, you'd go way above 2,000 degrees. So these are temperatures that are just beyond our imagination, right? I mean, you look at your stove, for example. The hottest thing you ever cooked is probably at about 425 Fahrenheit. That is nowhere near like the temperature of lava, obviously. It's only like here. So the temperatures, you know, that we work with are very different than these. When you take a bath or a shower, maybe your water temperature is about 110 Fahrenheit or so. Nowhere near these 1,000 marks here. But we'll go down. Certainly, these black lines represent those boundaries again. Every time you hit this curve, that's the temperature at that boundary. So the boundary of the stiffer mantle and the outer core is about 5,000 degrees C. If you keep digging down, the outer core, inner core, that's about 62, 6,300 degrees C. Now remember, how hot was the surface of the sun? That's right, it was about 6,000 degrees. So the surface of the sun is about the same temperature as the outer core, inner core boundary. Of course, if you went into the inner layers of the sun, you would get into the millions of degrees, they say. But, you know, interesting that we have those temperatures in common there. And by the time you get to the center of the Earth, the hottest temperature of them all looks like about 6,600 or 6,700 degrees C. Okay? So pretty spectacular things going on with temperature. Then we go to pressure, and this is equally mind-blowing, or should I say crushing. Anyways, here at the Earth's surface, we have 1 atmosphere of pressure on our head. And when it's going to rain, remember, it's lower pressure. And if you get older and you start to get arthritis, you might hear an older person say, oh, it's going to rain. I can feel it in my knees, my joints. Well, they're not crazy. Well, they might be crazy, but they're not crazy for feeling that, because as there's less air pressure, your joints expand, and it's a painful sensation for somebody with sensitive joints. Well, that's only, you know, manipulation of about 1 atmosphere. Look at the unit on the side of this chart, folks. That's in millions of atmospheres. Again, things that are beyond our comprehension. Let me give you an example. You guys ever go swimming? You swim down to the bottom of the deep end. You feel it in your ears, right? Well, that's about, 8 feet of water, let's say. If you swam down to the bottom of the ocean, right, the average ocean depth is 2 miles down. That's way more than just 8 feet. If you did that, the amount of pressure down there would be about, they say about 4,000 pounds per square inch. You can work this out mathematically. And that's like putting a car on the nail of your thumb. Right, an entire automobile on the nail of your thumb. What's going to happen to your thumb? Well, it's completely crushed. that pressure is still nothing compared to the pressure we're talking about here, because this is in the millions of atmospheres. All right? We talked about diamonds. Diamonds have to form under immense pressure, right? Well, a diamond, even at the bottom of the ocean, that's not enough pressure to make a diamond. To make a diamond, you need about 700,000 psi. I mean, that's just amazing. And in order to do that, you would have to go right around this range to start to make a diamond, right? So to make one Mother Nature-wise. If you wanted to make one in a lab, well, then you have to obviously reproduce this type of pressure, and that's truly amazing. So anyway, the story's the same. The deeper you go, the more pressure there is. Take a look, follow me here. So that's where we are. We say about 0 million atmospheres, only like 1 atmosphere, right? Keep on digging. To the bottom of the lithosphere, you get about 0.1 or 0.2. So that's about 100,000 or so atmospheres. Keep going down. The pressure just keeps increasing. By the time you get to the outer core boundary here, you're at about 1.5 million atmospheres. And by the time you get to the core of the Earth, folks, a crushing 3.7 million atmospheres. And it's interesting that the unit is in atmospheres, because that's a unit we're very familiar with, right? Earth has 1 atmosphere. But if you go to other planets like the gas giants, their atmospheres are much thicker. So you wouldn't have 1 atmosphere of pressure on you. You'd have a heck of a lot more. Whereas if you went to the moon or Mercury, you would have no air pressure on you because there is no atmosphere. So it's all relative to Earth's atmosphere, right? Everything's related to our 1 Earth atmosphere. All right? All right, so let's keep checking out our layers here. Can you do this graph on the side? What would this look like with your hands? What does that look like? Let me see. The deeper I go, the more pressure I'm going to get, and you have a classic direct relationship. Okay? Same thing with temperature, of course. The deeper you go, the hotter it gets. We talked about that. There are 2 very interesting areas here where the melting point kind of fluctuates where the temperature is. And this creates an interesting situation. So the outer core of the Earth, even though it's under immense pressure, it should be solid. But because it's so hot, it actually, we think anyway, is a liquid. So it's called the liquid outer core. Now the inner core is even hotter, so you'd think it would be a liquid as well, but no, now the pressure takes over because there's even more pressure, and it forces it to stay a solid. All right, again, we'll get into how we think we know all this stuff based on that seismic analysis later on, right? Waves behave differently in solids versus liquids, but that's, where the scientific community is at this point. What does this graph look like? You got depth on the X, temperature on the Y with your hands. Well, the deeper you go, the hotter it gets. So yes, you're talking about another direct relationship as well. And we'll bring that up for you. Right. Oh, sorry about that. Should be right like that. Okay. Okay. Check out a couple of other questions here. Describe the relationship between temperature, density, and pressure as depth increases. Well, the deeper you go, all of those things increase, right? So if I dig down, my density numbers get higher, and I can zoom in on that for you. Oh, this one's going to... Hang on one second. Sorry about that, folks. Give me one second. All right, so to address that question there, you have to go back to the reference table chart, temperature, density, pressure. So if I go back to the chart here, and I zoom in, you can easily see that as I get deeper, the densities are increasing. So not only will temperature and pressure increase, but so will density. Okay? According to the tables, which layer is a liquid and why? Well, if you go back to your tables, it'll kind of indicate. Remember, we have our liquid outer core, so maybe write it right in there. That's your liquid, and this goes back to a solid. The asthenosphere behaves kind of like a liquid, more like a jello. But the true liquid part is your liquid outer core. Okay? Okay. A couple summary questions. Take a few minutes on those and then check back in. Which graph best shows the inferred densities, right? So which one, what happens to density? Well, we know the deeper we go, the denser it gets, but it's not a smooth transition. Right? If you go back to your chart here, you can see the numbers kind of jump. You go from, let's see, the bottom of the lithosphere about a 3.0, then it jumps to a 3.4. And then it gradually increases to a 5.6, then it jumps to a 9.9. And then it gradually increases to a 12.12, and it jumps to a 12.8. So it's not a smooth transition. So you're looking for a graph that's got kind of a bump in the road between the layers, at the boundaries. All right? So go back to your chart here. And there it is, between the upper mantle and the lower mantle, you get that jump, that 3.4 area jump. Okay? The next one here. Earth's outer core is best inferred to be, well, hopefully you went through the chart. Remember, it's the liquid outer core, average density of around 11. If you forgot that, don't worry about memorizing it. The outer core density right there, 9.9 to 12.2, so an average of about 11. Okay. Number 3, which statement most accurately compares the crust to the mantle? Again, you got to run through process of elimination here. But hopefully you came up with the crust is thinner and less dense than the mantle. And we can, of course, go back and double check. Look at how thin that crust is compared to the thick mantle there. Okay? Number 4, the rock between 2,900 and 5,200 is inferred to be, well, 29 to 5,200. Zoom in once again. Well, oh, actually, I got to zoom in on the bottom of the chart there for a second. 2,900 to 5,200, that's the orange. So now go up, and let's see what that is. That is the outer core, right? And we're inferring that to be a liquid. There's your densities, etc. Okay? So an iron-rich liquid. Incidentally, if you didn't know the abbreviation for iron, you can go to your reference tables. It says iron here, but sometimes it just will give you the abbreviation. If you recall, that's Fe, right? That'll be on the bottom of the mineral chart, all the abbreviation for the popular elements. And the last one there, number 5, which statement correctly describes the density of Earth's mantle compared to the density of Earth's core and crust? Again, it's a process of elimination. You got to run through them. The mantle is less dense than the core, right? It's above it. But, of course, more dense than the crust, right? The crust is above it. So that's how that works. All right, please go through the lesson very carefully. Make sure you understand the chart very well. We're going to, dig deeper, if you will, into this topic. So make sure you're good to go. If you have any further questions, type them into the comment section below, or, of course, shoot me a remind. All right, folks, take care.